Hi, ladies. It's hard to believe it is the last week of school, and after today, there's only one more B day. So today, we're on the fourth day of working in Chapter 5, and we're going to be covering the last part of nomenclature. So normal outline, prayer, updates, no prime time, reviewing homework and questions. New content is naming acids, and then I'll talk about classwork and looking ahead. So let's start with Our Father. In the name of the Father, the Son, and the Holy Spirit, amen. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done, on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. Lead us not into temptation, but deliver us from evil. Amen. In the name of the Father, the Son, and the Holy Spirit, amen. So 2 classes left. Today is naming acids, and then Thursday we're going to just be practicing. So personal update, I really wasn't sure what to share with you guys today, so I went and I picked some older photos of some things that were kind of favorites of mine. So this first picture over here is from my honeymoon to we took a cruise, and one of the places we stopped in was St. Bart's, and this is looking from the top of like a hill there down onto a harbor, which was very pretty, really nice. This picture here is in Singapore. It's of a Chinese lantern at their Chinese Lantern Festival. And this is reflecting on some water, like a retention pond kind of thing that was there. I was really impressed with the fact that I was able to get that photo. And this was before we had digital. So this photo was not altered or anything like that. So that's one of my favorite photos. These next couple of photos are from a dive trip my husband and I took to Utila, and we've got a sunset here. We've got a whale shark and just a picture on the beach. The whale shark was definitely a highlighting moment for us. We were not diving. We actually went out on a fairly small boat, and we rode around for hours looking for the places where the birds were diving down to eat the fish near the surface of the water. And where there were large collections of those, that is where there might be a whale shark. So we got lucky and got maybe 90 seconds with the whale shark, maybe not even that much. And I was shooting film at the time, very small roll of film. I clicked as many pictures as I possibly could, and at least I got this one. So this was a whale shark from that trip, which was pretty cool. And this last photo over here is one of the first trips that we took with my daughter, Becca, when she was young. She wasn't diving yet. She wasn't old enough. And we took a trip to Belize and stayed there. And we went out to the Blue Hole one day, and as we were going out, we saw these creatures surfacing, and Becca was maybe 7 or 8, and she said, "Those are pilot whales." And the guide who was driving the boat was like, "No, those aren't pilot whales. We don't see pilot whales down here." And sure enough, we got a little bit closer, and they're pilot whales. And there was a mama and a baby looking up at us, and we got this one picture where you can see its eye. It was pretty neat. Quite an experience, unexpected. Wouldn't have expected to see them there. So just a collection of photos. So I have a different PowerPoint that I'm going to share with you today, which is something that we did over spring break. As I've told you before, my husband and daughter both like to play around with chemicals, and my husband's also a chemical engineer. And one of the things that they've done is done this thermite reaction. So we wanted to show it to you. This is not something you should do at home. But this is the skeleton equation for this reaction. It's Fe2O3 plus aluminum. And what we're trying to do is replace the iron in the oxide compound with aluminum. So you end up with the products being pure iron and aluminum oxide. So take a look at this equation, write it down. Is it balanced? And if it's not, you can balance it for homework. And I think that's a pretty good hint that it is not balanced. So take an opportunity to balance it, and I'm going to show you our thermite setup. So safety first, we conducted this outside in a fire pit. We use a protective plexiglass barrier because there was a very hot reaction, molten metal. We also use tinted safety goggles because when magnesium ribbon burns, it is very bright and it can damage your eyes. If we had stayed in school for another week, you guys would have actually done some experiments with burning magnesium ribbon, and I'm sorry that we didn't get there. The other thing we had was water to put out a fire just in case it was needed. And again, do not try this at home. This is not something that everybody should just be doing in their backyard. So here are our reactants. So this is the bottle of thermite, and you can kind of see on here it's Fe2O3 and aluminum mixture. This is what the powder looks like. It's rust colored. It looks very much like rust. There is also aluminum metal that's ground into a very fine powder in here, so you can't really see it. We use aluminum foil to line the flower pot so that the powder doesn't fall through the hole in the bottom of the flower pot, but it's not necessarily there to be a source of aluminum for the reaction. To initiate the reaction, we really need a very, very high temperature. So we have two ways that we've done this or tried this. One is using potassium permanganate and glycerin, and the other is burning the magnesium ribbon. And I'll show you what both of these look like. So here is the potassium permanganate. It's down here, and my husband is going to pour a little bit of glycerin, which is just glycerol, which is not a harmful chemical. It kind of looks like mineral oil. So you'll see this, and you'll see it doesn't take very long. And there it starts to ignite. It gets very hot very quickly, and it doesn't need anything else. It's just those two components. So we did that on the side just so you could see what that looked like. And then the other option is to burn magnesium ribbon, which we have this here, a piece of magnesium ribbon, and it starts burning, and it's very, very bright. I was kind of standing in a place where there was a lot of smoke coming to it. It was actually quite windy this day, but as you can see, it's white right at the place where it was burning, so it is very bright. And this happens to burn at 4,000 degrees Fahrenheit or 2,200 degrees C, so that is very, very hot. And we decided to use some magnesium ribbon instead of potassium permanganate and glycerin at this time, partially because it was windy and this was a little bit more reliable. So we've got a piece of magnesium ribbon that's sticking up and in here, and so we were able to light the magnesium ribbon here, and as it burns and it comes down here, it will start the rest of the reaction. So our setup is kind of something that was homemade. We've got this plexiglass barrier with this set of chains, and we've got two flower pots. The top one is the one that has the thermite and the magnesium ribbon from the last picture. And the bottom one was set up so we could collect the products, because my husband was actually trying to collect something that was a specific shape. And since you've got molten iron and aluminum oxide that comes through the bottom of the flower pot, we were trying to collect it in there. So here it is. He's going to light the magnesium ribbon, and we have our tinted sunglasses on, and the ribbon is burning. And once it burns, it starts going, and you can see quite a flame there. This is why we don't do this in the lab and why you shouldn't do it at home. And once the reaction is moving and the stuff is coming out the bottom, you've got that molten reactive products coming out the bottom. And you can hear my dogs barking in the background because we locked them inside and they weren't happy about it. So I come over, it's like settled down enough so you can kind of see the top. It's very, very hot. And I try to get a look at the bottom. You can kind of see the buildup of all the stuff that's down there. So then afterwards, this is kind of what it looks like. I took a few pictures right at that time when I stopped videoing. So you can see it from the top. You can see it from the side. This is really red hot. Then after things cool, which took a little while, the products are iron and aluminum oxide. Iron is magnetic, whereas aluminum oxide is not. So we've got the flower pot. This was the top flower pot. This is the stuff that's kind of come through the hole in the bottom of the flower pot, and it collected on to this trophy base thing that he had. So you can kind of see all of this. This is looking at the bottom of the lower pot. And we went and we looked at it, and you can see we put some magnets here and put them in a plastic bag because we didn't want to get them all dirty. And you can see that it's magnetic. And also the bottom of this thing was magnetic. But as we touched other parts of this blob of stuff, it was not magnetic. So we could discern that we now had some iron based on its color and the fact that it was magnetic, and we had all this other stuff where the aluminum oxide was not. So that is one reaction that we did. You guys had already seen the penny reaction. So for homework, balance that equation and just write it on one of your sheets. So chapter 5 and 6 main topics. Acids is the only thing left. I'm going to go over some questions from last class. So I was asked on page 15 the coefficient for number 1 for the iron is 2, and that is correct. Some things on 17 and 18. So 17, number 1, CaCl2 was a binary ionic compound. Chlorine becomes chloride, so we have calcium chloride. Number 14, we were given the name and we need to come up with a formula. So aluminum is Al plus 3. You get the plus 3 from the fact that it's in the column on your periodic table that has the plus 3 above it that you wrote. Chloride is chlorine, and it's in the -1 column. So when you crisscross, you end up with Al1, Cl3. And since you don't need the 1, you just have AlCl3. Then number 19 was iron 2 sulfide. So iron 2 tells you it's Fe plus 2. Sulfide tells you it's sulfur, and it is in the -2 column. So when you crisscross, you get Fe2S2. And you can simplify this, but you can only simplify or reduce ionic compounds. You can't do that with covalent. So you have FeS is your formula for iron 2 sulfide. Then I had a question on page 19, number 20, FeHCO3 2. So when you reverse crisscross that, you have Fe is plus 2 charge, HCO3 is -1. You've got to confirm that this HCO3, whatever it is truly has a -1 charge, because if you had reduced, you wouldn't see that charge to be -1. So HCO3 with a -1 charge is bicarbonate ion, -1 is the charge. So your charges were not simplified or reduced. So that allows you to know that this is Fe plus 2, which is iron 2. And this is the bicarbonate ion. So your full compound name is iron 2 bicarbonate. I also had a question on page 20, number 38, molybdenum sulfate. It's a transmission metal. You need a charge, and you can't do this without more info. So the way the problem was written on your sheet, without knowing a charge, you can't do it. So it should be molybdenum 4 sulfate. So knowing that, you have molybdenum with a +4 charge, sulfate, which is SO4 with a -2 charge. You can crisscross them, gives you MO2, parentheses, SO4, close the parentheses with 4. You can reduce because both of these are divisible by 2, and this is an ionic compound, so you end up with MO, parentheses, SO4, close the parentheses 2. I also had a question, general question, can you do these without making a table? And this was referring to balancing chemical equations, and the answer is yes. But most people are not going to find them easily, because once you get up to 4, 5, or 6 compounds in or elements in an equation, it gets too complicated and people can't remember all that stuff. So it is really much easier to write make the table. And some of you will find that you can do some of them in your head, and some of you will find that you just need to write them all down. But I recommend, as far as doing them now and practicing, and until you get good with them, I would keep on writing the table. I also got a question on page 19, number 19. CuNO2 parentheses 2. I'd go through the same process, reverse the crisscross. Cu plus 2, NO2 is -1. This is nitrate. The charge is -1, which tells us this should be copper 2 nitrite. Sorry, I have nitrate here. It is nitrite. And answer key was incorrect. It had copper 1. So answer key for page 12, balancing the equation. So you should be able to see here that the only ones that were balanced were number 4, number 12, and number 19. All the rest of them were unbalanced, and you didn't have to identify anything more than that. And if you colored your peacock, you should have ended up with something that looked like this. And the ones that I looked at that colored them in, they do look like this. So magenta pages 17 and 18, I had recommended you do 10 of these 20. And if you tried to do one and you couldn't get it straightened out, to just skip it. So I wrote up, so here are the answers. Pause it here, you can check yours. And then I have my work in case you don't understand. So I've got 1 through 5 here. And what I tried to do when I had to go through multiple steps is I did it in different colors. So the first step I did here in red, and I fixed the numbers here, and then I did it in green and I fixed the numbers there. So you can kind of see my steps as I go through it. So pause the video if you need to look at them. 1 through 5, 6 through 11, 12, and I started doing it and I didn't like how it was going, so I just stopped and I started all over. So 12 is down here. And then 13, 14, and 15. Okay, then I wanted to talk about 17. So on 17, it was a little trickier. So first, I fixed chromium, and that when I put the 2 in front of this, I end up with 2 chromiums and 6 oxygens. And then I fixed my oxygens, and what I really needed in order to do this, I had O2 over here by itself, and at this one, there's 2 of these, so there were 6, and I needed to get it balanced. In order to get it balanced, I really needed just 3 more, but 3 halves is not a whole number. So basically, I went through. I start here with the 2. There's not a number in front of this Cr2O3. I needed the 3 halves here. So I ended up going through and multiplying all the coefficients by 2. And once I did that, this 2 changes to a 4. The 1 that was there changes to a 2. And this 3 halves changes to a 2. And so then all my numbers of atoms end up being double what they were. I could have taken it a couple more steps, but I recognize that if I take it as 3 halves and then I just multiply everything by 2, it'll work out. So I ended up doing the same thing for number 20. Number 20 ends up being the same thing. So I start out with my reactants and products as being 2, 2, and 1. And my products 3, 2, 1, which means the only thing that was not balanced was oxygen. But when I do that, what I really need to end up with is 3/2 here, and that again is not a whole number, so I balanced it with 3/2. It was then balanced, but since that's not a whole number, I ended up multiplying all of the coefficients by 2. So that ends up being 3, and then 2, and then 2, and then 2. So if you did these, you can see what I did. If you didn't do these, make an attempt. Try to do them. Try to work through them. The steps are here, and you can take a look. These are two of ones that I would consider a little bit harder, but that doesn't mean that you're not going to see them sometime. So I wanted to do some more balancing equations for some practice today before I got into naming acids. So I'm going to work through a number of these and show you my steps, and then we'll get to acids. So for number 1, here's my equation, and I wrote down my number of atoms. And I need to try to fix H and N on the product side, because looking at that, there are a lot more on my reactant side, and H and N are only shown in this one product. So what I ended up having to do was multiply this one by a coefficient of 3. And once I do that, it ends up being completely balanced. So take a look, look through the reactants and the products, and verify that you get the same thing. Number 2. So number 2, when I start out with my equation, I have 1 silver, 1 fluorine, 1 calcium, 2 chlorines. On the other side, the number isn't here until later. 1 silver, 1 chlorine, 1 calcium, 2 fluorines. So the first thing I did is I looked at my numbers 1, 1, 1, 2, and 1, 2, 1, 1, and I can see that I've got to fix fluorine. So I decided to do that one first. So I put a 2 in front of here. When I do that, that means I now have 2 silvers and 2 fluorines. And after that, I realized, well, I've still got to fix my silver, so let me fix that on the other side. And I do that, and I've now got 2 for silver and 2 for chlorine, and at that point in time, it's balanced. So this is a pretty easy one. Number 3, well, there's 5 atoms, but it turns out when you count them all on both sides, they're balanced. This one is fairly straightforward. So counting them is also pretty straightforward. There's 1 zinc, 2 bromines, 1 lead. Nitrogen has 2 because of this 2 outside the parentheses. Oxygen has 4 because it's 2 times 2. On the product side, there's 1 zinc. There are 2 bromines. There is 1 lead. Nitrogen, there's 2 because of the 2 outside of the parentheses. And the oxygen, there's 2 times 2, so there's 4. So number 4, we have carbon, hydrogen, and oxygen. So on the reactant side, we start with 2, and then we have 4 hydrogens, and we have 2 plus 2, which is 4 oxygens. And then we have carbon, which is 1, 2 hydrogens, and then 2 plus 1, which is 3 oxygens. So the first thing I decided to do is try to fix my carbons, and when I do that, I need to put a 2 in front of here, and that changes the number of carbons on this side to be 2, and the number of oxygen is 2 times 2, which is 4, plus 1, which is 5. So you see 4 plus 1 is 5. And I decide I'm going to fix my hydrogens. So when I fix my hydrogens, I have to put 2 in front of the water. So now I have 4 hydrogens, and now my oxygens are 2 times 2, which is 4, plus 2, which is 6. And so now that looks better. And now I've got to fix my oxygens, which are last. And so then knowing that I have 6 over here, this is not right. I need 2 here. This should be 2. So you need 2 up here in front of the oxide. Okay, so I fixed that. So that should be a 2. So now we've got 2 oxygens plus 4 oxygens, which are 6, and that balances our 4 plus 2, which is 6. So then number 5, we've got calcium, copper, and fluorine. There's 1 calcium, 1 copper, and 2 fluorines. And on the product side, 1 calcium, 2 fluorines, 1 copper, and that's balanced. Okay, number 6 is a little messy. So when we start with this and we have no coefficients in front, we've got 2 hydrogens here plus 3 hydrogens there, so 2 plus 3 is 5. Then we have 1 sulfur. And then oxygen, we have 4 here plus 3, which is 7. So I wrote that here. Boron, there is 1. And then on the reactant side, there are 2 borons. Sulfur, there are 3. Oxygen, there is 12 plus 1. Hydrogen, there are 2. So the first thing I did was try to fix my sulfurs. Because I have 3 on the one side, I wanted 3 on the other, so I put a 3 in front of this coefficient. So that now changes all my numbers. So now on the reactant side in red, I wrote I've got 6 hydrogens plus 3 hydrogens, which is 9 hydrogens. And sulfur, I have 3 sulfurs. Oxygen, I have 3 times 4, which is 12, plus another 3, which is 15. And I still have the 2 borons. Then I say, well, I'm going to fix my boron because I have 2 borons on the product. So let's get 2 on the reactants. So now on the product or on the reactant side, my hydrogens are going to change. So I've got 3 times 4, which is 12, plus 6, which is 8. Or sorry, that's oxygen, which is 18. So that's 3 times 4 is 12, plus 6, which is 18. Hydrogens are 3 times 2, which is 6. Plus 3 times 2, which is 6, so that's 12. And borons, there are now 2. So now the things that are definitely off, our borons are looking good, our sulfurs are good, and now I've got to fix hydrogen and water. So hydrogen, the last thing is it's over on the product side is H2O. I need to get 12, and I have an H2, so that means I need 6 of those. So when I do that, I've now got 12 hydrogens, and let's just count our oxygens. So 4 times 3 is 12, plus 6 is 18, and now it's balanced. So that is 1 through 6. So what I'm going to ask you to do is do the next 5 on that page. So that's page 16 in your magenta packet. Do numbers 7 through 11. And I'm also going to ask you to do this page, which is 14. This is pretty easy because only one of the compounds is incorrectly balanced. It only has 1 mistake. So you circle it and put the correct coefficient next to it. And the letter that's below the compound actually gets put down here in the bottom of the page with the question number. So the first one they found, looking at the original balancing, there should be 2 coppers on this one side, so you need to fix that coefficient to be 2. So the letter I is going to go any place there is a number 1 down at the bottom. So here where number 1 is, we're going to put an I. Down here in the bottom, we're going to look, you can look at the next one, number 2. You've got 2 nitrogens on both sides, so that's correct. Here we have 4 hydrogens, and here we have 6 hydrogens. Well, that's not right. So you're going to have to change the coefficient here on H2, which is L. So where you have the number 2 here, you're going to put L, and you're going to fix that coefficient to be a 3. Okay, so I'd like you to practice a little bit more balancing some equations, and we'll go over those next time. So if you want to pause the video and just do those right now before we switch gears into naming acids, that might be a good idea. So naming acids. This is the last thing that you need to know how to name, and it is probably the one that we spend the least amount of time on. It's a really small section in your book. My daughter actually said that was one of the harder ones because they spent so little time on it. So we spent a lot of more time on ionic, and we typically spend more time on covalent, but I wanted to at least touch on how to name acids. So you have this in your packet, and it is page 31. And you've got a few things to fill in. So pause the video, copy the information down, and then resume and listen to me, because copying and listening to me at the same time is going to be more challenging. So pause the video and then resume after you finish filling in all the blanks. So welcome back. Hopefully you paused it. So going through this, many covalent compounds may also be classified as acids. So what is an acid? Acid is a substance that produces hydrogen ions when dissolved in water. We group and name acids by the anion of the compound, and this allows us to have two different groups of acids, and they're called binary and oxyacids. So binary are defined as being composed of hydrogen and another element. Oxyacids are composed of hydrogen, oxygen, and another element. And you'll notice the only difference here is the oxygen. And you will find that this oxygen and another element tend to be polyatomic ions. And we need to know our names of our polyatomic ions in order to be successful with this. So for example, we have HF, HCl, and H2S are examples of binary acids. So let's talk about the naming rules. So the first thing is we're going to write the prefix hydro. And then we're going to add the root of the name of the nonmetal to the prefix. And in this case, the first one, HF, the nonmetal is fluorine. So the root of that would be fluor. And you're going to add the ending ic to the end. And then you're going to skip a space and write another word, acid. So you would end up with hydrofluoric acid. So that's HF, is hydrofluoric acid. HCl would be hydrochloric acid. And H2S would be hydrosulfic acid. So in the oxyacids, we've got examples of HClO, we've got H2SO4, we've got H3PO3. So you're going to write the name of the anion leaving off the ate or the ite. So this HClO is, do you happen to remember? It is hypochlorite. So it says here, if the ending would have ended in ate, you're going to change it to an ic. If the anion ended in ite, you're going to change it to us, O-U-S. So this is hypochlorous acid. So let's take a look at some of the other ones. So down here at the bottom, we've got H2S. First thing is to ask, is it a binary or oxyacid? It is binary because it doesn't have an oxygen in it. So the naming is hydrorutic acid. So hydrosulfic acid. Then we've got H2SO4. H2SO4 is an oxyacid, so it's over here. We have to identify that the SO4 is sulfate. So because it is sulfate, it's going to change the ATE ending to ic. So and there is no hydro out in the front, so it is sulfic acid or sulfuric acid. HBr is binary. So this has the hydro in it again. So it's hydrobromic acid. HCN does not have an oxygen. So it's hydrogen with a polyatomic ion that does not have hydrogen. So this is cyanide. So it becomes hydrocyanic acid. And then H3PO4. So PO4 is phosphate. Phosphate gets changed to be phosphic. So it's phosphic acid. So in order to be successful with these, you really, really need to know your polyatomic ions. Okay, this is why I had recommended to you guys, even though we weren't in school, to try to work on those during spring break. And then every day right after spring break, I recommended trying to memorize those three, because you will not be successful at doing these without having your polyatomic ion sheet with you and having them memorized. And they're just going to be hard. So I want to work on page 32 with you. So if you don't have your polyatomic ions memorized or you're not confident, have your sheet here with you so you can use that as a resource. So on your chemical nomenclature sheet, there is a little summary here that tells you about if the root ending would end in "ide," how to name the acid with hydrorutic acid. If it's root 8, it would be root-ic acid, and root-ite, it would be root-us acid. So this is the same information as was on the previous slide, but this is, I just copied this right directly from your chemical nomenclature sheet that was handed, well, it wasn't handed out, it was posted as a resource back when I posted everything right after spring break, and it's still on P-Learning. So let's go through examples. I'm going to do these first 10 on how to get the names from knowing the formulas, and then I'm going to do the other 10 from getting the formulas from the names. And if you work through these with your resources next to you, it'll be very easy for you to do your homework. Okay, so on the left side, we have H2SO3 is the first one. So first we have to identify which type of acid. It's an oxyacid because it has oxygen. So what is SO3? SO3 is sulfite, so the ending will be OUS, so it's sulfurous acid. And I do see it as sulfus acid, but I think more people actually put the UR in there with it. So then the next one is HCl. What type is it? It's binary. So we're going to end up with that hydrorutic acid, and the root is chlor. So it ends up being hydrochloric acid. HClO2, that's an oxyacid. So we have to ask ourselves, what is ClO2? ClO2 is chlorite. So ite becomes OUS, so it becomes chlorous acid. HNO3, it is an oxyacid. What is NO3? NO3 is nitrate. So the ATE becomes IC, so we've got nitric acid. Number 5, H2CO2. It is an oxyacid. So what is CO2? That is carbonite. So carbonite becomes and changes the ITE to OUS, so carbonous acid. H2CO3, this is still an oxyacid. CO3 is carbonate, so carbonate becomes carbonic, so carbonic acid. H3PO4, it's an oxyacid. What is PO4? It is phosphate. The 8 becomes ic, so it's phosphoric acid. H3P is a binary, so we're going to have that hydrorutic acid, so hydrophosphoric acid. HF is binary, so again, hydrorutic acid, so hydrofluoric acid. H2S is also binary, so again, hydrorutic acid, so that becomes hydrosulfuric acid. Okay, on the other side of the page, I think these are a little bit harder because they're ions. We have to crisscross charges again, so let's go through some of these. Number 11, phosphorus acid. So this is an oxyacid because the OUS ending implies ite, so that would be phosphite. So that tells us it's going to be H and PO3, but we have to crisscross charges. So let's find out what those charges are. So hydrogen is +1. PO3 is a -3. So when we crisscross the charges, we end up with H3 and PO3. And there are no parentheses around here because we just end up with a 1. Number 12 is nitrous acid. It's an oxy acid because of that OUS, and there's no hydro anywhere. So it implies the OUS is an ite, so that would be nitrite, which is H and NO2. Crisscrossing charges, hydrogen is +1, nitrite is -1, so they're going to end up crisscrossing and canceling, so it's HNO2. Number 13, sulfuric acid. Again, there's no hydro out in front, so it's an oxy acid. The ic implies 8, so it'll be a sulfate. So you have H and SO4. Looking at charges, hydrogen's +1, SO4 is -2, so when you crisscross them, you get H2SO4. 14, permanganic acid. Again, on oxy acid, there's no hydro in front. So this has a per and an ic. That means it's going to be a per and an 8. So we've got H and MnO4. So when we crisscross the charges, hydrogen is +1, permanganate is MnO4 and it's -1. So we end up with HMnO4. Number 15, hydrocyanic acid. It's a binary because it's got this hydro out front. So it's going to be H and cyanide. So cyanide is Cn. Looking at the charges, hydrogen is +1, cyanide is -1. Crisscrossing them, you just end up with HCN. Number 16, hydroarsenic acid. It's binary because of the word hydro in the front. It's hydrogen and arsenide. Arsenide is just AS. So when you crisscross charges, H is +1, arsenic is -3. So you end up with HS or H3AS. And the -1 is over here under my thing. So it is a -1. Number 17, hydrobromic acid. It's binary because of this hydro. So it's H and bromide, which came from bromine, which is Br. So H +1 and Br is -1. So when you crisscross those, you end up with HBr. Number 18, hypochlorous acid. Okay, it doesn't have hydro in the front, so it's an oxy acid. So hypo and OUS means hypo and ite, so it should be hypochlorite. So finding the charge in the formula for hypochlorite is ClO with a -1. So again, crisscrossing the charges, they cancel and they're both 1. It's HClO. Number 19, chloric acid. Okay, this is an oxy acid. There's no hydro out front. Ic actually came from 8, as you can remind yourself over here. Ic came from 8, so it's chlorate. So chlorate is ClO3 with a -1 charge. So when you crisscross them, you get HClO3. And then perchloric acid, it's an oxy acid. Per and ic means it came from per and 8. So per and 8 is perchlorate, so it's ClO4, the -1 charge, and you've got HClO4. So again, take your time in doing these. Identify whether they're binary or they are oxy acids. If they're oxy acids, You got to know what the ending is back when we were doing our polyatomic ions, which is why we did that before. Okay, so for homework, I'm going to have you practice page 33 and 34. 33, you have the name and you have to come up with the formula. And then 34 has the formula and you have to come up with a name. And I'm going to suggest you do half on each side. Okay, there's quite a few of them here. And I've already given you quite a bit with some balancing equations, which I know take a little bit of time, but I want you to practice a little bit more acids. Since we are really coming to the end of the term. If you have more time and can do some more, it's not going to hurt you because it's only going to help enforce how to name these. So your turn-in work, which is due Thursday morning, is to balance that thermite reaction equation that was earlier in the video. You've got worksheets, purple, pages 31 and 32, which we just worked through, going through naming acids. And then 33 and 34, man, when I went through and edited, I got rid of the A. So at least half on each side of that page. Magenta, page 14 was the balancing equations, and do a couple of these balancing on page 16. I have a survey out there, again, with some questions and your address if you haven't already given it to me. And your bookwork is the last section of chapter 5, and there's a couple problems on naming acids. So if you're really struggling with it from what we just went through, take a look at your book and it might help you. Looking ahead, curation project is due at the end of the week. I'm not going to be grading them until the weekend. You had 2 more resources to put in there. And I don't know if I mentioned this last time, but these really have improved significantly from the fall. I don't know if you've looked back on some of the ones that you did back when you were first starting to write those little paragraphs about the resources. They were kind of clunky and not very well written, and for some of you, and now your writing is just so much better. And many people are finding different resources to use, and that's great to see. And it's showing like a level of maturity and a level of how far you've come in your science knowledge. End of the year, you'd normally be turning in textbooks, but you're going to keep yours. Okay, so unless you're not returning to Beaumont, please keep your chemistry book. You're going to use the same one in the fall. We've agreed that this is the best method instead of having you guys turn these textbooks in. It's going to be kind of overwhelming to turn them in, and then they have to let them sit for 72 hours and then come in and deal with them. And you guys should just keep your books. Use the same books next year. We're going to keep your goggles in the classroom because as of right now, I still can't go into the building. So if you are not returning to Beaumont, we'll make arrangements to have you pick them up when the school is open for me to be able to get into. And it may be in the fall. I don't know because I don't have any word yet of when we're going to get into the building. So next class on Thursday, we're going to review the homework. I'm going to review key points from this semester of chemistry, i.e. the things that you really need to know going into next year to be the most successful. And I've put out there on the survey, what else do you need from me? What do you want me to go over on Thursday? What can I best help you with? There's a few people who've asked me, kind of if they're going to look at some chemistry over the summer, what are the key things? And that kind of is going to tie into what are these key points. Based on past experience, P-Learning does get shut down over the summer. Edpuzzle is not going to be shut down. You're going to still have access to those videos. I've got those math videos up there. If there were points that you really didn't understand and you really need to practice, those videos are still up there. Remember, I went back and I did some things with unit conversions and some of the other things that people asked me to do. I went over the chapter 2, part 2 test up there. That's up there. They weren't required videos, so they're up there with in your account. You should be able to see them with having no due dates. So ladies, that is it for today. One more day after this, and then it is summer. So, ladies, have a great rest of your day, and I will chat with you again on Thursday.